Good afternoon. This is Schweitzer. We're going to do a little video here on an answer key to modeling neutralization reactions. I lost her here. Involving weak acids. So there's a couple little wrinkles here and things that, once you see if these wrinkles, they aren't so bad. But either way, so complete the molecular and net ion equations for the reactions below. All right. Hydrochloric acid. Now this is a strong acid. And sodium hydroxide, which is ionic and is therefore a strong base. We don't talk as much about the bases, but there's a strong base too, forms salt and water. So molecular equation is going to be HCl plus NaOH yields H2O, or sometimes people call it HOH, which is perfectly fine. Looks a little bit better with H and OH. Sometimes that looks nice. And then we have NaCl. All right, the ionic here is just going to be H plus OH negative yields water. So that is a bit of review from our last page, and nothing really new there. So those are strongs. How do we go about dealing with things when they're involving weak acids? Okay, so again, you should be trying something on your own and seeing the difference. Now I've drawn a model out for you here. Everything's complete. You just have to now say, well, if this is what's happening here, what would these equations look like? All right, well, we have HF now. Big difference here. Okay, this is a weak acid. What's different about this versus all the other acids we've drawn out? They aren't showing the products. Now remember, this is a weak acid. Only thing that is actually acidic is the H plus ions. Are these guys acidic? No. But these guys undergo hydrolysis and plus water in a water beaker. So, all right, yields H3O plus F negative. But this thing is in a battle back and forth, and it's extremely reactant favored, and we get a very, very small amount of products. So small, in fact, that sometimes we don't even show them there. That being said, they're still present, and this is slightly acidic. These little guys here are just so nasty, all right, that if there's even a little bit of them around, we notice them. Either way, so that being said, all of these, when these guys get neutralized, more of them will push over. So in the end, just because I'm not showing the acid present, it is available and it can be neutralized. So weak acid, all right, notice that, okay, one of these guys grabbed one of those guys essentially and formed a water molecule. And what else do we have here? Well, I didn't show everything here, but there's going to be an F negative here. Okay. And then what else we got here? All right. Well, it looks like this guy here grabbed onto this guy here and formed a water molecule. And an F negative. I should probably include those in there. And then we have HF. Nothing left to grab onto, and here it is. Okay. And of course, we have our two spectator cations. All right. There we go. So how would we write this out? Okay, well, it's just going to be HF plus NaOH yields NaF plus H2O. There we go. Net ionic. Okay, so what's happening here? Well, it looks like an OH is grabbing an HF. That's how we do it. HF plus OH negative. Now, even though the F doesn't have anything, really isn't doing anything to it, it's still very closely tied to this thing. It does change slightly. So it's going to produce water molecule and F negative. What's the spectator here? Only Na plus is the spectator here. Na plus is the spectator. And that's all we got for that guy. So we've now shown a model of this guy and then how we model these. They're a little different, especially with those weak acids. They are held together as opposed to separating them. So that's a big difference to strongs. All right, so now on this guy, okay. On this one, I modeled it this way, and I want you to write out the beakers, okay. Excess hydrocyanic acid is neutralized by potassium hydroxide. Again, you should be trying these beakers out before I give you an answer. I want an excess though. So I got one of these guys. We'll grab HCN. Notice I'm keeping it together. To form water molecule and Cn negative. Another hydroxide grabs an HCN to form a water molecule. I'm going to go HOH here, just for fun. Cn negative. Another hydroxide, we've got a bunch of them here, grabs an HCN, very constant, a little more concentrated, produces a Cn negative H2O. And then another one, the last one, grabs one of these guys, Cn, forms an H plus, H2O, and a Cn negative. Now it says excess, which means that I want more acid than base. I'm going to add in another HCN here, just for the heck of it. And we'll put this guy right here. That's my excess acid right there. Of course, I have 4 spectator ions, cations, 1, 2, 3, 4. And you notice my positives and my negatives match in this beaker, which is always, should always be that way. All right, so we've modeled it back and forth between the two ways. You've now seen the ways that they do these things. So you got a chance to try some more on your own here. All right, ammonium chloride reacts with lithium hydroxide. Complete the beakers below based on the reaction. Okay, so ammonium, which is going to be NH4 plus, that is a very common idea, common substance. It's in your houses, especially. Ammonium and ammonia, which is NH3, are two little sort of brothers that they flip back and forth between each other as they get, neutralized and as you add an acid or base to these, and they flip back and forth. And you'll see this guy here. Here's ammonium chloride. Here's this guy. So take a look how I wrote this out. Okay. All right. Let's predict the beaker. I got ammonium, which is this guy is a weak acid, and this guy here is a weak base. Known weak base, known weak acid. So ammonium is a weak acid. It will grab on to a base, and it will form ammonia, NH3, and now notice here that H will give, this guy gives the hydroxide of water. H plus, so it forms water. Okay. And there you go, and that's located right there, and right there. Okay, and then this guy here grabs onto this guy here, and we forms NH3, and of course a water. And then we've run out of ammonium chloride. Everything else is just left to kind of hang out and watch. Chlorides, we got cations, 1, 2, 3 lithiums, and I have an excess hydroxide ion. Positive negatives match, we're good to go. All right, now write out the molecular reactions for the beakers taken below here. Okay, so now let's reverse this process again here. Let's see what we got here. Okay, so we have an ammonia grabbing onto an acid to form ammonium, and I have another ammonia grabbing onto H plus ion to form another well, here we got it. It forms ammonium. And it looks like there's an excess of that guy, which is located there. And we have a few anions here. Add specter ions, please. Okay, so this guy should be these chlorides that didn't do anything, so they should be right here. Notice the beaker has positives and negatives that match. That's always nice. All right, let's write the molecular equation. It's going to be, well, I got ammonia, which is just NH3. And I'm going to react that with HCl, hydrochloric acid. That, by the way, just a reminder, as you drew this, this definitely is a strong acid based on the model that's separated. HCl yields NH4. All right, and you could, in this case, you could draw H4Cl if you wanted to. There we go. And I would draw this as aqueous. Okay, AQ there, it's AQ. Meaning it's dissolved. That's the way you do it. All right, and then this guy here would be just NH3 plus H plus yields NH4 plus. True or false? Every neutralization reaction must make water. Wow, you would have thought until this moment you would have thought that was true. But look at our problem here. There's no water being produced. And if you understand that's just an H plus jumping onto something, then maybe you'd realize that, oh, okay, this is a unique example maybe I never thought of or didn't know about, but no water is being produced. Okay, so is that it? Oh, there's one more left here. Okay, little challenge question here. All right, we got this product beaker here. What is the original acid and what's the original base that would be there? Okay, well, looks like the acid we're talking about is HF, and the base we're talking about is just going to be NaOH. NaOH. Okay. So they're going to form, in this case, F negative and water, right? And of course, you could do NaF if you want to show a molecular version. So what do we got here? So it looks like we have this guy and this guy were formed, and this one. All those guys came together to form this one. So we have, in this case, we have Na plus and OH negative, okay? And then we have here HF. Everything I've drawn here is located in the circles here. Remember, this is just HOH. So this guy and the Na are there. This guy and the H are located here. All right, so let's do that again. I have this guy here, this guy here. These are the products. So we had to have an Na plus. We have to have an OH negative. And we have to have an HF. And it would appear also there's one left, those guys that wasn't able to react. And there we go. What's the salt produced here? Would be NaF, sodium fluoride. Okay, that's my salt. All right, thank you very much. Hope this was helpful.